video, sir?
Yes, ma'am. Hello. Hello. Ma'am, I can't hear you.
Will join. They are informed and
Okay, ma'am. Okay.
they will be joining, sir. Like I can see them. We have sent reminders. So let us begin, sir.
Okay. So I
Deepak,
welcome
sir,
all.
thank you so much. Oh, please carry on, sir.
Okay. Everybody, I welcome you to the SOA lectures, SOA weekly academic lecture series of 2020 to 23. This is the 12th lecture that we are conducting. And here we have Dr. Deepak Ranjan Nayak, who is going to present his topic on COVID detection from the X-ray images. So we will be we will be continuing into the topic in a little bit later. First of all, I would like to introduce all of you to our university, that is SOA University, which ranks in the 16th in the university category and 27th in the engineering category. And here is a information video or introduction video about our university, which I would like to play to you. So please um, look at your screen. Hello. Okay, with this, we will be starting our webinar. First of all, we are very proud to have Dr. Deepak Ranjan Nayak as our guest lecturer. He is currently appointed as Assistant Professor at the Department of Computer Science and Engineering in MNIT Jaipur. Prior to this position, he was Assistant Professor in the Department of Computer Engineering in SBNIT Surat. He worked as a postdoctoral fellow in IIIT DM Kanchipuram, Chennai. He received his PhD degree in Computer Science and Engineering from National Institute of Technology, Rourkela. He has published over 50 articles in peer-reviewed journals and conferences of international repute. His current research interests include medical image analysis, machine learning, deep learning, pattern recognition, and computer vision. His publications have more than 1500 citations and H-index with H-index of 21 and I-10 index of 32, according to Google Scholar. One of his papers was included in ESI highly cited papers. He has received he has received 2020 CMES Young Research Award from the Tech Science Press for outstanding research in computer modeling and simulation. He is currently implementing one research project funded by SERB DST Government of India in the field of medical image analysis. He serves as a reviewer of more than 60 peer-reviewed journals such as IEEE Transaction on Circuit Systems for Video Technology, IEEE Journals of Biomedical and Health Informatics, IEEE Transaction on Neural Network and Learning System XR to name a few. He has also served as technical program co-chair, publication chair, session chair, committee members of several conferences of international repute such as IJ, CNN, ICO, NIP, and CVIP. He is a member of IEEE. He serves as a editorial board member of International Journal of Imaging System and Technology (WILI) and a guest editor in Mathematical Bioscience and Engineering Journal. Now I request Dr. Deepak Ranjan Nayak to present his talk to all of the listeners.
Yeah, thank you so much for the kind introduction. Let me share my screen.
Yes, yes.
Yeah, I've already shared my screen. Is it visible? Can you please confirm?
Yes, it is visible.
I think participants have already joined, right? So shall I start?
Yes, more participants are coming, but we should start.
Okay, thank you. So thank you, Dr. Divya Sundar, for the opportunity. I feel privileged and honored to be a part of this lecture series organized by ITER Bhubaneswar. Right, I am a little bit surprised by looking at the growth of the ITRs. For the last couple of years, it's really great to know. Uh, that's fine. So the topic of my talk is the role of deep learning. Basically, I have written AI, then I have striked it out. Then role of deep learning for COVID-19 detection in chest radiography images. So basically, I'll be focusing on the importance of the cutting edge AI technologies, which is deep learning, along with some of the medical imaging technologies, how they both are combined together in identifying COVID-19, right? As one such a case study, right? Both can also be combined to detect various types of diseases. So mainly I'll be focusing on COVID-19 detection. I'll not be focusing on other applications. So in this particular talk, I will start with a few interesting things. Please try to interact throughout the lecture if possible, right? Sometimes I may ask some questions or maybe I may try to interact with some of you. Please try to interact. So I'll start with image interpretation, and I just want to show you that how difficult sometimes medical imaging is to interpret. And then I'll be talking about the importance of the CAD system or the importance of AI or the cutting edge AI technologies like machine learning and deep learning in the field of medical image analysis. Then I'll talk about one of the most popular type of deep learning architecture that has been extensively used in many computer vision tasks, which is nothing but convolutional neural network. And also I'll talk about the different ways to use convolutional neural network to solve a wide range of medical image analysis problem. And the kind of problem which I've chosen for this talk is a very recent problem that we all know, that how to detect COVID-19, right? Although we have a gold standard method called as RT-PCR. So is there any other alternative methods available which can also detect COVID-19, right? Or maybe within 5 minutes or 10 minutes, because we all know that the gold standard method is a time consuming process that we will look into it. Also, I'll talk about the importance of attention mechanism in this field of research. And at the end, I'll talk about the current challenges and the future research directions in the field of medical image analysis. So I'll start with image interpretation, right? So now you can see there is one picture which is there on your screen, right? And if I'll ask you, can you interpret this image? I mean, I just want to know that what is there in this image? Can somebody just let me know quickly, because we have limited amount of time. What is there in the image? Yes, please, if possible.
It's a sunset image.
Okay, it's a sunset image, right? I mean, if I'll ask the same question to somebody else, maybe I may get different answers from different. But most of the contents in this particular image is known to us, right? And if I'll show you one more picture over here, right? We're trying to understand the content of the image basically, right? If I'll show you this particular image, although we know most of the contents from this image, but this image seems very unnatural. Am I correct? I think this picture is not obeying the law of nature. Is that correct?
Yes.
Somebody has artificially created this. That's true, right? So although we are well known with all the contents of the image, there is something, I mean, wrong information present in this image. But almost all the contents are well known to us, right? So let me show you one more picture here. And if I ask you what is there in this image, right? And I'm just expecting something interesting answer from you guys. All right? Could you able to understand a single content of this picture? Yeah, I hope definitely you will find difficulty in interpreting this image, because this is not a natural image which you can capture through our mobile camera or maybe some DSLR camera. Rather, this is a medical image, right? Histopathological image, basically used to identify breast cancers, right? So now, if you look at the content, is whatever the content is present in this image, which is very, very difficult for us as we are not, you know, expert in this particular field. Maybe some radiologist or maybe some doctors can better say that what is there in the image, right? But again, what they're doing is they're manually interpreting the image, right? Again, there are some limitations with the manual interpretation process. Also, we'll talk about the same thing in the coming lectures, right? So this basic, I mean, this image tells us how difficult sometimes to identify or to understand the content of a medical image rather than the natural image, right? And there are so many minute details which are present in this image. Sometimes even doctors may miss or radiologists may miss such minute details or such change in the minute details in the image, which may lead to some of the disease, right? So that was all about how to understand the content of the image, otherwise called as image interpretation. So now let us talk about what is learning. What is learning? To make you understand what exactly learning is, right? So I have two pictures, right? So the picture which is there on the left hand side, you all know. If I ask you one simple question that can you recognize these two images, that we all know, right? The answer is pretty obvious. Yes, the picture which is there in the left hand side is nothing but the statue of Sardar Vallabhbhai Patel, or Statue of Unity, you can say, right? And the picture which is there on the right hand side is nothing but the statue of Dr. APJ Abdul Kalam. The answer to the first question is pretty obvious. But if I ask you that how do you recognize these two images? Have you ever asked yourself that how do you recognize an object that's surrounding you? How do you recognize these two images? Can you please tell that how do you recognize these images? Yes, I just want a quick answer from you.
From our memory, we try to map the facial structures. That's how we know who this person is.
So that means what you are saying is you have seen these objects earlier, right? May not be the exact picture. Maybe you have seen the photos of Dr. APJ Abdul Kalam earlier, or you may have seen the photos of, I mean, both of them, right? Earlier, somewhere.
Yes.
And
Yes.
have you intentionally stored in your memory, or that was automatic?
That
You have
was
not intentionally stored,
involuntary.
right?
Yes.
Yeah, that's the inherent capability of our human brain, right? And now what I want actually, the God has given us this power to us. Our brain is a massively parallel system. Whenever it sees some new objects around us, and what it basically does, it tries to capture some of the important patterns from such objects, stores in our brain, and next time when we see that particular object, it tries to capture, it tries to match whatever is already embedded in your brain. Within a fraction of a second, you could able to tell, yes, this is the photo of Dr. APJ Abdul Kalam, right? That's what the brain is, and we're trying to make the human brain, right? And that's what that's all about the concept of machine learning, right? What we're trying to do now, we're trying to solve the same problem with the help of a machine, right? We're trying to solve the problem with the help of a machine, but our machine is not that intelligent. We have to make it intelligent, right? So the way we learn from the experience, we learn from the past examples. In the similar way also, the machine learning algorithms will learn, right? So we need a lot of samples from both of the categories, and then we'll try to feed the samples on the algorithm, and based on the training samples, you will build your model, and then you can test your model. You can check the effectiveness of your model by using the testing set you have, right? Like we learn. In a similar way also, we can learn our machine, and that is where actually the concept of intelligence lies in. That's what the concept of machine learning is all about. And what we want in place of these natural images, can we have such set of medical images, and then can we develop machine learning models or deep learning models to recognize the disease, right? Whatever doctors are doing, can we do the same job with the help of a machine? Right? Yes, we can. We can also try to capture some of the relevant informations or patterns from the medical images, and then we can process those images with the help of some of the advanced machine learning algorithms or maybe deep learning algorithms to detect some sort of disease, right? And it doesn't mean that we are here to replace the doctors. We cannot replace the doctors. So it's the job of the doctors to provide us the data, basically the level data or the annotated data, and because we need data to develop a model, right? And I'll talk about in a few moments the importance of this CAD system and all, right? So here are some of the examples of the medical images, which is not looking like natural images like this, like this, right? So we are not well known to all the contents of these images. Here are some examples you can see of X-rays imaging, MRI imaging, microscopic imaging, basically used for identifying blood cancer and all. Similarly, here are some other examples of ultrasound, PET, and CT scan, right? So what it seems that it is not that easy to understand all the contents or maybe the abnormalities, whether there is an abnormality present in this image or not. right? So we always need the help of the doctors to label this data, and what we need is the label data, right? Because mainly we are focusing on supervised learning algorithms. Yeah, of course, we can also design unsupervised learning algorithms, right? That also I'll talk about later on. Maybe whenever I will talk about the future challenges in this domain, then I will be talking about. And we all know the importance of this medical imaging. Now doctors can see inside a patient, right, without having to cut them open. I mean, most of the parts of the image. So in earlier days, doctors used to perform operations to know what happened to a particular part of the organ. But now, with the advent of these medical imaging technologies, right, doctors can see inside of a patient, right? So that's the beauty of these medical imaging modalities. And the interesting thing is why we people are interested, although we are from the computer science background or from the electrical background or from the electronics background, why we are interested in solving this type of problem, because the output of these medical imaging modalities in the form of digital representations. And we all know that if it is in the form of digital image or maybe videos, with the help of digital computer, we can process those images. And when we talk about interpreting these images, right, doctors, if you are an expert, if there's an expert doctor, then he can or she can interpret the images or the content of these images. But yes, of course, there are several problems they may find if they are detecting or they are manually detecting some disease with the help of these medical images at a larger scale. And the process is basically a tedious process, time-consuming process, and of course a very expensive process. And it always requires scale supervision. You always demand, right? It always demands the domain experts, basically the experts, and which you may not find in the rural areas as well. Right. So here are some of the limitations of the manual detection process, and this basically help us or tends towards developing, right, automated detection algorithms or systems which may be preferable for fast, reliable, and accurate diagnosis. And the term which people have been using is called as computer-aided diagnosis system. It has a lot of importance nowadays. Right? The application is not limited to academics. Right now, most of the companies, starting from Microsoft, Google, right, are also working towards developing effective computer-aided diagnosis systems for identifying different type of disease. I have also a few couple of slides just to show you that how industries are also working in this particular field, right? And basically, the goal here of developing the CAD systems, and we need the help of the machine learning algorithms as well as the medical imaging technologies, right? Of course, because the input will be the medical images or videos in this case, and we'll be using machine learning algorithms or deep learning algorithms, right? And the basic goal here is to help the radiologist or the medical experts in accurate interpretation of the image. Right, so they can easily cross-check their diagnosis with the help of the CAD systems, which you can develop with the help of this cutting-edge AI technologies, right? And it has a lot of importance, as I talked about, right? And the most important point is it can lighten the burden of the increasing workload. Let's say we all know that if you just go back to 2020 or 2021, the number of cases, right, COVID-19 cases was too high, and you will not find also such an expert or radiologist, right, expert radiologist who can easily identify whether there is a presence of COVID-19 in the chest radiography images or not, right? And one of the most important thing is it can also reduce the inter and intra-reader variability. Right, this is a very simple concept, inter and intra-reader variability. You know that also if you sometimes if somebody is suffering from some disease, if he or she visit to some doctors, right, or two or three doctors, if, I mean, different doctors may have different opinions on the same report, right? And also if you go to the same doctor twice or thrice, the same doctor may have also different opinions, right, on the same report. That's the problem of inter and intra-reader variability. In that case, you will not find in case of computer-aided diagnosis system. Right, and there are various types of problems actually that are currently being solved, right, in medical image analysis domain. And one such popular type of task is classification, basically disease grading, where your task is to classify a medical image into different categories, right? Basically, whether there's a disease or not, or maybe tumor grading kind of thing, whether the tumor is of grade 1, grade 2, grade 3, grade 4, like that. It's basically a classification problem. Can be a binary classification problem, can be a multi-class classification problem. Similarly, also we have something called as object and lesion detection problem, where it's a kind of object detection problem where you need to identify one particular region where there is a lesion or where there is a tumor, right? And segmentation is one of the also most popular type of medical image analysis task. Also, we have a registration and content-based image retrieval systems. For all these tasks, you will find computer-aided diagnosis system, right? And here are the examples of the segmentation problem, which is a little bit tricky. And also there are architectures, right? Like a convolutional neural network, which I have talked about. Also, there are specific convolutional or specialized convolutional neural network that has been developed for solving segmentation problem, right? Where you will find most the output is also in form of images. The major difference between the classification and the segmentation problem is classification, the input will be image, the output will be a label, right? I mean, basically the disease name or whether there is a disease or not. But in segmentation problem, the input is an image, the output is an image. You can see the input images in the first row here and the output images in the second row, right? So I'll talk about it later on. Yeah, this part also I have to focus because mostly those who are pursuing their BTech and MTech, they must know that there are so many industries currently focusing on medical image analysis problem, starting from Microsoft, Google, right? You may go through their groups or their project name, right? Maybe the Microsoft's Hanover project is mainly focusing on solving medical image analysis problem for identifying the tumor progression and the development of the programmable cells. So similarly, you will find also there is a group, crucial group in Google who are also focusing on solving medical image analysis problem, right? Where they are trying to develop some of the machine learning or deep learning algorithms to detect various cancerous tissues. In India, you will also find there are a lot of startups, right? There are a lot of startups. They are only focusing on solving medical image analysis problem. And Niramai is such a company, right? Who is only focusing is in a Bangalore-based startup actually, right? Who is only focusing on one type of problem, which is breast cancer, right? And what they're trying to do now, they're trying to develop some of the softwares based on machine learning, computer vision algorithms, right? And they are not using this. Breast cancer can be detected through different types of medical imaging technologies like mammograms, ultrasound, right? Thermal imaging and all. And what they are focusing is thermal imaging. And what they are claiming is their solution is a low cost, accurate, automated, right? That's what they are claiming. And their imaging method, whatever they're using, that's the thermal imaging, is a radiation free. But mammogram is a kind of X-ray images. We all know how harmful it is, right? So you will find a lot of startups and industries also. You will get a lot of opportunities in industries and if you are working in this field, right? So we all know the importance of machine learning, right? In identifying the disease, right? Here is a graph between the number of papers and the year. That means the number of papers that has been published in the last decade, right? Based on medical image analysis. If you look at the number of papers, right, that has been published is increasing exponentially over the years, right? And as we are talking about deep learning nowadays, why people are showing so much interest, right, in applying deep learning algorithms over machine learning algorithms. Let us first talk about what are the different stages that are involved in a machine learning based CAD system. Then we'll talk about some of the weaknesses and advantages of both the categories like machine learning based CAD system and deep learning based CAD system. In machine learning based CAD system, you will find a multi-stage pipeline architecture, right, to come up with the final decision. The input images will be in the form of medical images. And the very first stage you will find is a pre-processing, right? Why this pre-processing is required? The pre-processing is basically is to simply remove the unwanted informations that are present in the image. If there are some noises that are present in the image, you have to remove the noise, or else you may not extract the relevant information from that image, right? I mean, your main goal is to extract important patterns, right, from the input images given to you. And because of the presence of the noise, you may not able to extract such type of important information from the image. So what you need to do, you need to remove the noise, but you need to be very careful, right? Whenever you are applying the pre-processing techniques, right? It should not also lose some of the information, right? So, and you need to check whether whether the pre-processing is required for your problem or not. And the next is ROI segmentation. So segmentation itself is an independent problem for which also you will find a lot of CAD systems in the literature. But sometimes this ROI segmentation can also be used as a pre-processing stage in a machine learning based CAD system, where you need to only identify a particular part of or particular region where there is a presence of abnormality in the image, right? So no need to extract the patterns or the features, right, from all over the image. Rather, you want to only extract features from the important part of the image. And that's what is ROI segmentation. And the most important type of the most important stage in any machine learning based CAD system is a feature extraction. So where you will find a lot of problems. Why? Because what type of feature, the question here is that what type of feature you would like to extract from this. So if you're an expert in this domain, then based on your expert, and if you have gone through 100 papers or 50 papers in the literature, then you may simply tell that yes, this type of features may work well on my problem because I have seen the success of this type of features on other problems, right? But you cannot guarantee that yes, these features will definitely work in a problem. This is a challenging task here. That what type of feature? The feature can be a shape-based features, geometric features, color-based features, maybe local features, global features, image transform-based features, texture features, could be anything, right? The problem here is how to identify a best or an appropriate feature extraction algorithm, right? For that can extract some of the discrimination information from it or from the given images. And this feature reduction is a kind of optional stage, you can say, because if you find that not all features are important for your problem, then you may remove some of the irrelevant features, right? Or you may remove some of the redundant features if you have extracted, right? And sometimes this feature reduction stays, there are two types of actually algorithms which you can apply over here. One is a feature subset selection algorithm, and one is a kind of a feature dimensionality reduction problem like PC and LDA. And at the end, you can use a classification algorithm. You might have heard about 10 or 12 10, 12 or 15 number of classification algorithms like support vector machine, neural network, naive Bayes, K, nearest neighbor, random forest, descent tree. There's so many, ensembling based classification algorithms and all. But if you go through the literature, you will find more than 100 types of classification algorithms exist. Again, there is a problem here that which classification algorithm you will select, because there is no such theorem that has been proved. You will find that yes, I have to use only, or that is problem dependent basically, right? So what you will face here, the problem is to how to select an appropriate feature extraction algorithm and appropriate classification algorithm, because these two are the vital stages in any machine learning based CAD system, right? And after finding out, let's say, the best feature extraction algorithm and the best classification algorithm, right, by using maybe some technique, maybe you may use some trial and error process, right, to find it out, or whether the combination of this feature extraction and classification is giving better result or not. That is again a major concern in this type of CAD system, right? And the kind of features which we are extracting actually here in machine learning based CAD systems are called as hand engineered or hand crafted features, because we are using some sort of prefixed feature extraction algorithm to extract the features. Right. So what we have seen in this case that this machine learning based CAD system has involved with a lot of stages, and in every stage you have a concern, right, in identifying an appropriate algorithm. That's what the problem we are facing in machine learning based CAD system. And these type of problems you will not find in deep learning based CAD system, because in deep learning based CAD systems is basically end-to-end learning system where you will give input at the one end and you will get the output at the other end, right? And basically it eliminates the conventional steps of machine learning. So that means no need to extract the features. In machine learning based CAD systems, whenever you are extracting the features, you are not looking at the output of the image. Simply you are extracting the features, you are applying an algorithm over all the images, and you are extracting some sort of the patterns. You are not looking at the output images, and we are not even changing the features. We are looking at the output of the images. That means we are not learning the images, right? And that's what is possible with the help of deep learning algorithms, that this deep learning algorithms basically tries to learn the high level features, right, directly from the images. And we do not need this manual feature engineering, whatever, right, we are doing in case of machine learning based CAD system. And it can also easily retrain. That means if you have developed a deep learning algorithm, let's say for solving a classification problem, an image classification problem, and now your friend wants to use your model because let's say he's or she is not from computer science background, he's from let's say mechanical background, but he wants to solve a problem, maybe still image classification problem he wants to solve, and he wants to use your model. But whether it is possible or not, yes, it's possible. He can also use your model to solve his problem by making few modifications. We'll talk about it, how to use convolutional neural network, and what's the concept of what is the concept of transfer learning, right? And the two most successful and popular type of actually deep learning methods are actually autoencoders and convolutional neural network. But the convolutional neural network is very famous and very successful. That has been used widely for solving basically image and video centric problems, right? So I should not actually spend some time on on in discussing the concept of convolutional neural network and all, because you might have heard about this term earlier, or somebody are using, right? Most of you might be using this convolutional neural network for solving a couple of computer vision problems, right? But the question here is, given a problem, whether I should go for machine learning and deep learning, right? This is a common question which always strikes in our mind. So how do you decide that whether I should go for machine learning and deep learning, right? It all depends upon the kind of problem which you are solving. If your data is actually small, so of course why you will go for deep learning models, because deep learning models always require a very large amount of data and it is computationally intensive. That means to provide a reliable result, right? Deep learning models always demands a large amount of data. Now the question here is we're talking about solving medical image analysis problems where you will not find any large scale annotated medical, data set like ImageNet, for which you will find a lot of new architectures in convolutional neural network, right? So because data acquisition, basically medical data acquisition is bit difficult. You cannot capture through your mobile camera these medical images, right? And even sometimes to collect 100 images, right? You need to wait 2 years or maybe sometimes 1 year, right? Only 100 images. But this ImageNet is such a data set, right, which was proposed in the year 2010, right? 2010. And in that time also, the data set was containing 2 millions of the images, right? But now we are not having any such data set yet available, right? Which is a large scale in case of medical imaging. And deep learning models always demands high amount of data. So then the question here is, how can we use deep learning algorithms in the presence of limited amount of data? Is it possible to use deep learning algorithms, right, with the help of limited amount of data? Yes, it is possible. There are few strategies available for, through which you can use deep learning algorithms, right, even in the presence of the limited amount of data. Fine. Yeah, I have a couple of slides, I think, on convolutional neural network, how it looks like, and the various popular convolutional neural network, convolutional neural network architecture, right? This is a sequential convolutional neural network, right? Actually, the concept of this convolutional neural network can be tracked back to late 80s. 1980s. These are not the new concepts which we are talking about. It's very interesting actually to know the history of this convolutional neural network, from where actually the concept brought and why we are using this convolution, what is the relationship of convolution and why it is working well. Now we all are talking about explainable AI, explainable deep learning models. So previously people, researchers were using convolutional neural network as a black box. So now there are different ways to explain what is happening inside convolutional neural network, right? So the concept of convolutional neural network is not at all a new concept. It was introduced in late 80s by Professor Leekon. He's also one of the, what you can say, the inventor of convolutional neural network, right? So then the question here is why it has taken 3 decades to impact the vision community. So we can say it was the right algorithm at a wrong time, because at that time there was no such storage capacity to store the images, and of course there is no GPU facility also that time, right? So that is why initially the Professor Leekon and his group got a lot of criticisms from other researchers that what you have developed, it requires almost 1 month of time to train a model and like that. So, but later we all know the heroes of deep learning, and they all have been awarded Turing Award, right? Which is a kind of Nobel Prize of computing. We all know that, right? And the kind of architecture they proposed, right, in the year 1998 is called as LeNet. Basically, was developed to solve digit recognition problem, which was a 10 class classification problem. The classes are from 0 to 9, right? And in the output layer also you will find 10 number of neurons, right? If you look at the architecture here, this is the LeNet architecture, right? It's a sequential CNN architecture. So later you will find various different types of convolutional neural network, not exactly sequential one after another, right? And it basically consists of different layers, mainly convolutional layer and activations layer like ReLU and maybe some other variants of ReLU and all. And pooling layers you will definitely find. And at the end, you will find fully connected layers, which are actually costly layers. And why the name is so called fully connected, because all neurons in one layer is connected to every other neurons in the preceding layer. And that's why the name is so called fully connected layer. At the end, you will find a submax layer, right, where you will find the probabilities values of all the classes. And based on the highest probability value, we usually assign the class level, right? So this is all about the story behind this convolutional neural network, right? And if you are a beginner to this convolutional neural network, so you may find a lot of videos, or maybe you may find a lot of resources that are available on the internet to learn what is convolutional neural network. And you must learn also the working principle of each and every layer of convolutional neural network to understand, right, every popular architecture. That's very important to learn, right? And suddenly after 1998, you will find a huge gap, right? And then in 2012, we found architecture called as AlexNet. Right, the major breakthrough happened in the year 2012 after 1998. Then thereafter, you will find a lot of architectures by introducing some concepts, new concepts into the architecture, or by modifying something into the architecture, or by reducing the number of parameters required by the architecture. Because when AlexNet was proposed, the number of parameters required by AlexNet was around 60 million. So if the number of parameters are 60 million, and let's say you are solving a problem where there are only 1000 images or 200 images, you can easily see the difference between the number of images and the number of parameters. This may lead to some overfitting issues. And we all know if my model will suffer from overfitting issue, then obviously my model will not generalize well. That means my model will not perform well on the on-scene data. So that is why over the years, researchers have tried to develop, right, lightweight models, means the model having less number of parameters with improved performance. And you will find some interesting concepts in Google Net called as Inception Net, right? Otherwise called as, and you will find something called as Inception module, which is basically developed to extract multi-scale features from the images. I'll talk about the importance of multi-scale features even while I will discuss the COVID-19 problem, right? So similarly, we have resonate density. These are all popular kinds of CNN architecture. I must not spend much time over here, right? So you will find the importance of all these models, right? And we'll have already talked about what is ImageNet, and there was a challenge actually on 2010 onwards, right? And initially for 2 years in 2010 and 2011, the winners are not, I mean, based on the machine learning, basically the winners models are based on machine learning. But later in 2012, when AlexNet came into the picture, if you look at the error rate, right, suddenly dropped from 25.8 to 16.4, right? That's a huge gap, right? And then over the years, you will find the importance of this GoogleNet, VGG, ResNet, DenseNet, ShuffleNet, Efficient, and all. Right. So, and one more thing also here, I must highlight that over the years you will find the models, right? When AlexNet was designed, it was only containing 8 layers, right? I'm talking about the layers which only contains parameters, right? You will find several other layers also in the architecture, right? But the more you see the number of architectures that has been published over the years, right? From AlexNet to ResNet, the number of layers, right, are going to increase over the years. So does it mean that deeper is the better always? No, it's not like that. Always deeper is the better, right? And now the question here is, although there are so many different types of architectures available in the literature that has been extensively used for solving a wide range of computer vision or medical imaging problem. So can we develop also our own architecture and all? Yes, this is a question to all of you, that can we develop our own architecture? Now the question is, can you simply increase the number of layers and say and claim that yes, this is my model, right? In Electionary, if you will increase the number of layers, then can you claim that it is my model? Actually, no, people will not appreciate actually, right? If you simply increase the number of layer, so there must be some reason behind it why we have increased the number of layers, right? So always deeper is not the better, right? If you go through the paper, I mean the best paper of RADIOGRAPHY, right? There it has been proved that deeper is not always the better one, right? So you must have some intention behind this. Yeah, from the last couple of slides, I've been talking about the importance of deep learning over machine learning, right? And also I would like to show you one interesting graph which we have derived, right, from the Scopus database. So I've considered actually 2-3 database. And if you look at here, I mean, we have considered the paper that has been published in the last decade, right, based on machine learning and based on deep learning in the field of medical image analysis. So now if you look at the graph, right, this blue curve basically denotes deep learning, and this orange curve denotes this machine learning, right? If you look at just after 2016, the number of papers that are published based on deep learning, right, is higher compared to the number of papers based on machine learning. But it seems that people have shown a lot of interest in applying deep learning algorithms rather than machine learning algorithms nowadays, right? So then what are the different ways to use convolutional neural network? There are basically 3 ways. One is like AlectionNet, you can design your own model, that is called as training from the scratch. You have to train, you have developed your own model. You have to train the model from the scratch. That means you have to initialize the weight, random weights, and then you have to apply some sort of optimization algorithms to train the weights or to optimize the weights, right? This method, is a highly accurate method because the model will train based on only your data, but it always demands a large scale data set and of course high computational resources, right? And coming to the second strategy, what we have is a transfer learning, which is very, very important. Now, in transfer learning, what we basically do, we use some sort of pre-trained convolutional neural network. That means now, let's say I'm solving a problem of brain tumor classification, which is, let's say, a 5-class classification problem, where there are only 5 number of classes. But I'm planning to use, let's say, AlectionNet to solve my problem. Yes, if you go back to the architecture of AlectionNet, you will find 1,000 number of neurons at the output layer. What does it mean? That it is solving 1,000 classification problem. AlectionNet was designed, right, based on this ImageNet dataset, and it was designed to solve a 1,000-class classification problem. My task is a 5-class classification problem. And the simplest way is to simply remove the last layer and replace it with a 5-layer based layer. I mean, 5 neurons, a layer with 5 number of neurons. And then I will fine tune the model. Here I'm not starting with the random weights, rather I'm starting with a predefined weights or pre-trained weights, I can say. And then I'm trying to fine tune the model based on the images, whatever is given to you, right? So that is what is actually transfer learning, and there are various ways to do transfer learning actually. So you may only fine tune the last layer, you may fine tune the all fully connected layer, or you may also fine tune all the layers, or you may freeze all the layers and only fine tune the last layer. There are various ways, that all depends upon the kind of data set you are handling. Whether your data set is a larger one or a small one, right? Based on that, you need to decide that how many layers you want to fine tune. So transfer learning transfer the knowledge of one network to another network to solve a similar type of problem. You have to solve a similar type of classification problem only, right? So similarly, I mean, this transfer learning can also be applied for other types of problems, right? So if you have developed your model, this AlectionNet was designed for classification problems. So what you can do, that you can solve any image classification problem with the help of AlectionNet, right? Using this transfer learning strategies. But this transfer learning strategy does not demand much amount of data like the training, like the first strategy was, and it also demands fewer computational resources compared to the first one. That is why you will find a lot of applications of transfer learning in the field of medical image analysis. right? Because we are having limited amount of data in this field. And the last one is using, it is also, the last one is also one form of transfer learning, you can say, and it is nothing but using of the cell pre-trained CNN features. That means here, what we will do, rather than using a feature extraction method, whatever we have seen in case of machine learning based CAD system, what we will do, that we will use AlexNet that has already been trained on ImageNet dataset. We'll use AlexNet to extract the features, right? You can extract the features from any layer of the AlexNet. Mostly we used to extract from the fully connected layers. You may also extract from the last convolutional layer and store it in a feature vector and repeat the same process for all the training images. And then you will be having something called as a feature matrix. And then you can use any classification algorithm that you have been using, right, in machine learning based concept. Right. And the last one, I cannot guarantee that whether it is working well or not. And if you are having only 10 images, even 50 images, you can also go for the last one, right? The last category one. Fine. But there is no guarantee that whether, because as you are not fine tuning, as you are not modifying the weights based on the data given to you, so there's a less chance that this strategy will perform well, right, on the data. But that you can check whether it is giving good result or not. If you're having limited amount of data, you may also go for the last one and check whether it is working well or not. Right. So we're slowly moving towards our main goal of discussion, which is COVID-19 detection. Right. So we have seen the importance of, cutting edge technologies, AI technologies, which is convolutional neural network, and as we are focusing on medical imaging, right? And also we have seen the importance of medical images. Now we'll see how these medical images together with convolutional neural network are useful in identifying COVID-19, right? So I'll not talk about the importance of COVID-19 screening, the history, the literature, everything about COVID-19 we all know, and when it was declared as a global pandemic and all, and from where it started, and what was the virus name, everything, right? What are the symptoms? These are all things which we all know, right? As we all have been experienced with this. And there are so many areas where you will find the applications of AI, right, in COVID-19, not only in only detection and prognosis. You will find there are a lot of areas where AI can contribute to fight against COVID-19, whether it is early warning and alerts, tracking and prediction, treatments and cures, and social control. Everywhere you will find the applications of AI, right? So why actually we're talking about this COVID-19 detection, although we have RT-PCR, which we all know is the correct method and the gold standard method. The problem with the RT-PCR is, yes, it is time consuming and it's manual. There's a possibility, we all know that if it is manual, there's a possibility of misdiagnosis, right? So that is why we are mainly focusing on some alternatives which can also help us in detecting COVID-19. And later you can verify the same with the RT-PCR method, right? So soon after actually this COVID pandemic, the researchers have shown the effectiveness of chest radiographies images, mostly X-ray and CT images for identifying COVID-19, because they could able to find some radiological indications in the X-ray and CT images of the COVID-19 patients and the healthy patients. And suddenly they proposed and they published few papers in some of the medical journals. And from that day, we have been working in this particular field. We have been facing also, we faced a lot of problems initially to get the data and all. But later we found some benchmark data and all. Also, there are few challenges which we have not yet addressed. Right, I'll talk about it. And what we have seen is, yes, of course, X-ray and CT images are very useful in identifying COVID-19, because X-ray and CT was very famous earlier days, right, in identifying pneumonia. And similarly, we know also there are some similar characteristics, right, between this pneumonia and COVID-19. There are some radiological indications. You will find less amount of expert radiologists who can identify this COVID-19 with the help of course, this chest radiography images, right? And mostly will not find such experts in rural areas and all, right? And I have also few pictures to show you for both X-rays and CT scan. Although we have mainly focused on CT scan later on. Initially, we have focused on X-ray images, right? And there is of course difference between X-ray and CT images, right? Because X-ray images is more cheaper, right? I mean, now within 200 or 300 you can easily capture your image, right? X-ray images, but let's say CT is more expensive, right, compared to that. But in CT you will find more what you can say, the excellent resolution of the images, right? And pretty easier to identify the image, I mean, whether there is a COVID-19 presence or not. So here are a series of X-ray images. If you look at here from the first row to the second row, the series of X-ray images, right, of an 80-year-old woman, right, who has, I mean, who has suffered with this COVID-19, right? And over the day, this is the image that has been captured on day number 5, day number 7, 11, 14, 17, and 18. You will definitely find some changes in the images that are mostly, right? If you look at the white shadow, right? Basically, the shadow white, basically it is called as uh, ground glass opacities, right? Ground glass opacities, the term which they are using, and that one there is something called as pulmonary consolidations. So what you can see that these part are longs, right, which is visible here in the first image, right? Both are black in color, you can see easily, but over the time you will see there are a lot of white shadow, right, is over those longs, right? Both the longs over the time, over the time, and now even the last image, you will not able to see any parts of the longs, right? It's very difficult to see. That means, and on the day 18, actually, unfortunately, she died, right? And that is clearly visible from the X-ray images, and you can find the changes, the radiological changes in the images over a period of time in the X-ray images. So similarly, in the city, these are the examples of the city image where you will easily find out some ground glass opacities, basically. And here you can see there are some changes, and also white patchy shadows you can find in some images. These are some of the radiological indications. Actually, what I'm trying to show you, these are some of the radiological indications which you will not find in the, I mean, healthy persons, right? If you capture the images of a healthy person, and that we need to capture. Sometimes these are, you will find very small changes, right? If you are capturing the images, right? Maybe at the early stage of COVID-19, right? So then there will be no significant difference between the healthy image or the normal image and the abnormal image. So, but the person is suffering from COVID-19, right? And the very interesting thing is, even if the person is, there are some asymptotic cases, right? You might have heard about, right? The person is suffering from COVID-19, but you will not able to find him, that whether he is suffering from COVID-19 or not. Those are called as asymptotic cases. And it has been reported in some paper that I'll also show you those papers, right? From where we actually get all these informations and why we have been working in this field since last 2 years, actually, right? So because there are the few papers that suddenly they reported that there are clear radiological findings available in the CT images, right, for the patient, I mean, having asymptotic behavior, right? That's a very important thing about this, right? So you will find thousands of papers that has been published using convolutional neural network, right? Uh, for COVID-19 detection, of course. We've been working since last 2 years, and we have also published a couple of papers. These are the 4 papers which we have published. One of the papers, I think Dr. Divya is also one of the author, because he was also one of the team members of when we started actually solving this problem, right? So in one my intern, if you can see his name three times, right? Amog Joshi, I'll talk about him later on, who is actually Amog and what he's doing right now, right? So you can see these papers actually that has been published in IEEE transaction. One is in IEEE transaction, and one is in SM transaction. One is in IJCNN, which is one of the peer-reviewed conference in the field of neural network, right? And one is biomedical signal processing and control. So if you want to know more about these papers and all, so you may go through our paper, and codes are also available, right, publicly. And I am interested in highlighting only one paper, which we have recently presented in IGCNN at Italy, right? So our main goal actually was to develop a multi-scale based architecture, right? Multi-scale CNN based architecture, although you will find the same concept in some of the popular CNN models like Inception and all. But the way we developed this multi-scale by looking at this, lightweight architecture that is pretty different from others, right? And then these are some of the building blocks that you might have seen in case of ResNet, DenseNet, right? Probably in DenseNet, if you implement DenseNet, those who have implemented, they might have seen that DenseNet, although is helping in deriving multi-scale features, but sometimes it also helps in deriving some of the redundant features, right? Because the output of one layer is connected to all other layers, right? So that's the problem actually in the dense block, although it has been very popular, but only the problem here is the redundant features, which you do not want, right? So what we initially planned to develop such a module which is lightweight compared to all others that are published. And if you look at this structure here, the structure is pretty different. We are not using different types of filters, maybe 3x3, 5x3, 7x7, not like that. We are only using 3x3 and 1x1 filter. Right, and these 3x3, 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 and combinations of 3x3 are helpful in identifying the multi-scale features from receptive field of different sizes, right? And this has been arranged in such a way that although it looks like this, dense block, but it is not like that. Actually, in dense, the major difference between our module and their module is, if you look at the DenseNet module, that the output of one layer is going to the, input to the other layers, right? I mean, all other layers, but here you will not find such case, right? And the basic goal was to develop a multi-scale model, basically the multi-scale module, and by keeping the model is lightweight, right? And one of the important thing in DenseNet, what we have seen, the dense connections is within the local block, right? So we have proposed this one, right? The multi-scale local feature extraction block, this block. And then we thought of initially simply combining these layers, right? And we have not got any interesting results from this. And then we thought of connecting these blocks globally, like they have connected locally, right? So that means the major contribution here is this block as well as the global dense connections among these blocks, right? That's why the name is so-called global dense feature instruction block, right? And we have 5 different blocks here, and you may find here the global connections among the block. I mean, the global dense connections among the blocks basically help in learning the global representations, right, from the city images. Yes, this is a whole architecture, whatever we have developed, and this is architecture summary. Here's the comparison with some of the popular architectures, and also we have compared with MobileNet, which is also very famous for its lightweight architecture. And if you look at the number of parameters and the size in MB, basically is comparatively less, and the kind of result which we have got, right, is really interesting and is promising compared to all other methods. These all methods have been applied on the same experimental setup and the same data set as well. So we have got an improved result on using our model, right? And here are some of the visualization results, right? Because today we're talking about explainable AI and whether the convolutional neural network have extracted the correct features or not, and how it gives good results actually, why it gives, right? So to prove that, we have generated heat maps with the help of GradCam, right? Where you can see these are the images of that have been captured from the COVID-19 patients, and these are the images, right, that have been captured from the healthy persons. And what you can see that yes, my model is focusing on the important parts, or you can look at the lesion parts or the regions, abnormality regions here and here, right? Although it is not exactly focusing on the part which is missing here, right? But still it is focusing on the parts where there is a presence of COVID-19 or where there is a presence of abnormality. That's what you can see from this picture. And for the rest other pictures, it is not focusing anywhere. Why? Because those are not right? These are the images that are not captured from the COVID-19 patients, which gives some indication that yes, my model is focusing on correct features and it is deriving correct features from the images. But here there is a scope that can it only be focused on the lesion area rather than focusing on the all areas, right, in the lungs. Yes, it is possible with the help of the attention mechanisms, which people are right now using with the help of this convolutional neural network, right? Yes, there are some limitations in these works, whatever we have done. The data set size was pretty small initially, but later we have used a bigger data set. And the problem here is the data set which we have used that doesn't, but basically that do not include the patients with different stages of COVID-19. Right now, there are few data sets available. I mean, just now released, where you will find the different stages of COVID-19, which is actually important, and the patients with asymptomatic cases. Right. So these are the things or the points which we'd like to check our model, right, in future, that whether our model is performing well, right, with these asymptomatic cases or not, right? Because it's very, very important. And as I mentioned earlier, that there are abnormal findings, clear abnormal findings you will find in CT images of asymptomatic COVID-19 cases. And here are the two papers where you will get to know that whether there is a presence of abnormal findings in CT images of asymptomatic COVID-19 patients or not, right? Attention mechanism, as I told you, that was very, very important nowadays to focus on the relevant regions and to ignore irrelevant regions from the images, right? And like we do usually human beings, right? We always used to focus on salient regions in the complex scenes, right? And that's what is the major goal of attention mechanisms. I'm not interested to talk more about this attention mechanism. Just I'd like to show you one result which we have got with the help of the proposed attention we have made, and this paper has been published in 29th International Conference on Image Processing. This is a image processing conference that we all know, right? And if you look at these two images, right, the images which is there in the second row and the third row, you will find the major difference between, right? This is the output of the model without attention mechanism, and this is the output of the model with attention mechanism, right? So without attention, my model is focusing on, right, the important part as well as some of the unimportant parts. But here, if you look at, my model is trying to focus on only on the important parts. That's the difference between this, right? This attention based model and without attention based model, right? And also we have compared with some of the um, state of the art, right? State of the art modules. I mean, basically attention modules, right? That have been published in 2021, 2022, and we've got better results compared to them, right? So the major challenges, what you will find in these cases is a lack of training data sets, which I've already talked about, because these are not such natural images which you can capture through a mobile camera. And the annotation is itself is a bit, a difficult task, because you will find always doctors are busy with their work and it is their job to level the data. We cannot level the data, but nowadays, there are some interesting technologies, right, that are coming up, and in computer vision, how to learn your machine with a limited amount of data, right? And let's say you are having limited amount of level data and many data without levels. You have collected from somewhere. Maybe you are having some friends in some of the hospitals. They've given you some of the images, let's say, and that are on-leveled, right? And doctors are busy and you want to use those images. So what you will do? So do have such technique which can annotate, or which can level the on-leveled images which you have with the knowledge of the level images you have, right? That's the concept of the self-supervised learning people are using nowadays, right? And now people are talking about transformers and all, right? And how to use those such heavy CNN models which demand large amount of data, right, is also a major concern in the field of, or a major challenge in the field of medical image analysis. Handling class imbalance is also one of the important problem in this field, because what you will find in this case always the number of cases, the number of abnormal cases you will find is less compared to the number of normal cases. So that means if, let's say I am solving a problem, a medical image analysis problem, where I'm using a data set. My data set contains 1,000 images, but my 1,000 images, but one class belong to 100 images. I mean, one class basically contains 100 images and another class contains 900 images. And of course, there's an imbalance problem here, right? So can I use or can I develop such a model which will not be biased towards the majority class, right? That's what the problem of imbalance is. So people have been using some sort of traditional techniques like, there are some majority based concept algorithms. There are data augmentation techniques people have been using to solve this type of problems. But now the current trend of solving this type of problem is a GAN, generative adversarial network, right? So can you explore some sort of, recent convolutional neural network architecture which are being developed for solving this type of problem or not? Right, and including the clinical features and the imaging features. So what I have shown you, right, in many of my slides are nothing but we have been talking about the imaging features. We're not talking about the clinical features. So can we combine the clinical features, which has also some relevance in identifying some sort of disease? Can we combine this clinical features with the imaging features to come up with a final decision? Yes, it is possible, and this is the current trend what people are doing in this field, right? That can also be done with this COVID-19 problem. And here are some of the journals and conferences in this particular domain of research where you will get the latest findings in this research. And here are a few references, right? And I must thank Amog, right? My intern, actually, he was not my intern. He was a kind of student who have done intern under my guidance for 2 years, right? Mr. Omar actually was working with me since 2020, and he was very interested in, when he joined actually as an intern with me in 2020. He was very interested to go for MS outside. From that day onwards, he was very serious, and he joined my lab in the year 2020. Then in 2022, what he is doing is doing MS in Arizona State University, US. Uh, Doing MS in Arizona State University, anyone can do, that's fine. But the kind of facility what he has got is extraordinary. I've never actually heard about it later on. So he has 3 publications with me, right? That there's a joint work with me, and now he is doing MS in Arizona State University for free. He's not paying a single rupee to Arizona State University, which usually takes 60 lakh, per a MS student. And on the top of that, because of his publications, their dean from computer science and engineering has offered him one position where he is getting $2,000 per month, which is very unusual in Arizona State University, right? And what he was telling that, sir, this was the first time somebody is getting from the first semester, and from the first month of the first semester is anyone getting $2,000. I mean, MS, right, is usually PhD student gets $2,000 in US, right, for doing the PhD. But MS student getting $2,000, it's something extraordinary. And getting this news on the eve of Teachers' Day was very emotional for me, right? It is the story of a private college student, right? I took 4 interns in the year 2020, and he was the only one from the, I mean, private college, rest all others from NIT and Triple IT. And he was from a private college from Bombay. And now if you look at his story, and it's really interesting. I must thank also Dr. Dibya, who has also been instrumental in solving problems. We had a lot of discussions during that COVID period that how you can solve the problem and all. Thank you once again, Dr. Dibya and your team, for inviting me. It's a really, for me, it's a great honor. Thank you so much.
Thank you for your presentation. It was a nice presentation. And thank you for all the patience people are having and listening to you. I would like to ask about 2 things. If anybody having any doubts, you can post the question, and I will be trying to convey that to Dr. Deepak. Now, my question is that what's coming next? We have gone through CNN, right? We have gone through even what the AI has been very much development. So, what is going to be the next stage where we can focus on for the research that the student can do research on, so that they can publish some papers or they can do good work?
It's really a good question actually. That's the same thing actually always coming to our mind also. What should we do next? Because there are a lot of papers which are coming nowadays. What
Yes.
we can do next is one direction is the attention which I've shown you, because people are talking about explainable deep learning models or explainable CNN. And one thing is people are right now focusing on mainly transformers, right? Why transformers? Because they have shown the limitations of convolutional neural network basically. So we need to go through those papers where they have mentioned what are the limitations of traditional convolutional neural network. Although it has been very successful in many applications, there are also some limitations in convolutional neural network. Sometimes, I mean, basically, when CNN fails, there are also few problems, right? We can easily fool CNN, that you also know. हम CNN को मतलब fool भी कर सकते हैं, right?
Yes. Yes.
By giving some interesting patterns or by designing some input images by ourselves.
Yes.
And
That.
can we handle those type of cases with the help of CNN? What researchers are claiming, it is not. So that is why they are right now talking about transformers, which is again a new era started, the transformer era. Right now, this year, if you try to go through the conferences, I mean the top conference basically, so you will find 70% of the articles are using transformers, not using CNN.
Okay.
So the world is going so fast actually. So we need to identify the problems or the failures of the architectures like CNN and all. And if it is working well in our problem, then there's no problem actually. We can also find out some, like we have find out one issues that many of the earlier models have not used the multi-scale concept, right, which is very important. That's what we did, right? And now attention has become an important part, and in transformer what you will find is the major component is attention again, right? So that is what is the current standard. And also like there are some other areas where we can focus, that how to decide because how to decide or how to design a CNN, because designing CNN itself is a very tough task, right? Whenever you are adding a new layer, there are maybe 10 possibilities that I mean what type of layer you should add. So can we have some sort of algorithms which can give us a better algorithm or better architecture, right? Because
So
100 types of
basically, we are
architectures.
going to design neural network that will design other neural network.
That's true. That's true. Which is called actually neural architecture search, NAS problem
Okay.
nowadays people are solving, right? I mean, people are trying to design neural network using neural. That's true. That's true. It's very
That's
interesting.
very interesting one. That's very. Anybody having any other questions? You can please ask or post.
No,
Uh,
thank you.
yes. Anybody else asking anything?
Thank you.
Okay. So we would like to conclude this session. I would like to thank Dr. Deepak Ranjan Nayak for giving his valuable time from his busy schedule. And I hope everybody has learned something from his talk. I would also like to thank Dr. Debahuti Mishra ma'am, HOD CSE, for organizing the webinar. I would also like to thank organizing team members, Dr. Sarada Prasannapati sir and Dr. Madhuri Rao ma'am, for their support. Lastly, I would like to thank all of the participants for their participation in making this webinar successful. Thank you all. Now we can all leave the meeting.